today in particular, it's really just up here. This is the overview of physical climate science. So we have fossil fuels, we have greenhouse gases in the atmosphere, and we have how that affects temperature. So it's the fundamentals, it's the basics of what everything else kind of stems from. And so I'm going to be explaining this as best I can, kind of using a single two-dimensional diagram of the Earth. So kind of you think about the important components of the Earth. We have the land surface, we have the ocean, that's going to be important. We have ice, so we have glaciers on the land. We also have sea ice, so that's frozen water just sitting on top of the ocean, as opposed to a glacier is on top of land. We have plants. The terrestrial biosphere is an important component of the Earth system. And then, of course, the atmosphere. And then we kind of can, in our hypothetical model here, we can kind of put a cap on the atmosphere and say, okay, everything else on the outside is space. And so we talk about gases in the atmosphere a lot in this class. And so I think it's useful to kind of take a step back and think about, okay, what is the atmosphere actually made of in the first place? And what are the, we talk about these particular gases a lot, like these greenhouse gases, CO2, you'll hear probably the most of. But is that the largest component of the atmosphere? So we have, when I say like what it's made of, you could say air, right? But what does air mean? It's, we're talking about elements here, right? So we think about our periodic table of elements. We have nitrogen right here. By the way, we'll be talking about molecules a lot in this class, so it's kind of worth it to think about the periodic table again if you haven't thought about it since junior year of high school. So what is this, what does this 7 mean here? 6 is 6 protons, 7 is 7 protons, 8 is 8 protons. And so it's useful to remember that that's the definition of what these atoms are, right? So so here is carbon, C, N is nitrogen, O is oxygen. And those words are just names that we have for atoms with various numbers of protons in their nucleus. So if you have an atom with 6 protons in its nucleus, that is we just call that carbon. And if you have an atom with 7 protons in its nucleus, we just call that nitrogen. So it's true that most of the atmosphere is nitrogen, diatomic nitrogen, N2. And then oxygen is the second most abundant. And then we have H2O, so bringing in some of our hydrogen atoms here. And then also oxygen, of course, is in H2O as well. And then argon is another atom that ends up being roughly around 1% as well. So what we talk most about in this class, like CO2, is just a tiny fraction of the atmosphere. So we talked about that last time, that it's about 410 parts per million, which is about 0.041%, right? Percent means parts per 100, cent means 100, so century, like century. And you can just kind of do that math in your head, that if it's 410 parts per million, then that would mean it's 41 parts per 100,000, 4.1 parts per 10,000, 0.41 parts per 1,000, 0.041 parts per 100. So just a tiny bit of our atmosphere is actually CO2. And then another greenhouse gas that we'll talk about is methane, CH4. So carbon is also in methane. And so a lot of times when people talk about carbon emissions, they're talking about both of these, carbon dioxide as well as methane. And they're referring to the carbon in both of those molecules. But methane's even smaller concentration. And nitrous oxide is another greenhouse gas that we'll talk more about, which is even smaller. But the point here is that most of what the atmosphere is made of, we don't actually care about in terms of climate change because it's just nitrogen and oxygen, I will show you why, are not gases that really matter for changing the climate. So what we do care about for climate class, for climate change class, is methane, CO2, and water, and in particular water vapor. So that's water in gas form in the atmosphere. And so we have all these molecules in the atmosphere, and let's think about why these are important for climate. So it's going to have to do with the Earth's energy budget. So where do we start when we talk about the Earth's energy budget? Where does almost all of the energy on Earth originate from? From the sun. That's right. So where else could we get energy? Yeah, geothermal is one. Geothermal is not energy that you can trace back to the sun. So that's from like radioactive decay. Someone said wind. Wind actually can be traced back to the sun. We have no sun, we're not going to have wind actually. And then, yeah, so then there'd be a little bit from other stars, right? So at night, when you're looking up at the night sky, you have other stars that are not the sun, that are, the fact that you can see them means that they're bringing energy to the Earth. But yeah, so we start with the sun. The sun is emitting energy towards the Earth, which we call light. And it turns out that the amount of energy coming down towards the Earth is 342 watts per square meter. So you think about like a 100 watt light bulb. So it's about 3 times that per every single square meter on the surface of the planet. And that would be averaged over the entire surface of the planet and averaged day and night. So when you're actually like outside in the day, it's more like 1,342 watts per square meter coming down. And that's, you know, watts is, it's a joule per second. It's a rate of energy movement per unit time. And it's just the standard way that we measure energy movement. So that's our basis. That's what's coming in. And notice how I've drawn this, that this arrow passes through these molecules here. So I've done this intentionally, where the molecules are sitting on top of the arrow. And what that is trying to communicate is that those molecules are not interacting with that light coming in. It's just passing right through them. And we can think about this just intuitively, that if it's a clear day and there's not pollution in the atmosphere, and you go up, and I wouldn't recommend this, but if you stare at the sun, then you are just, there's nothing in between you and that light coming down from the sun, right? It is, you can just see straight through the atmosphere, and you can see the sun perfectly. So if these molecules were interacting with light from the sun, then it would be obscured and you wouldn't be able to see it. But we do have other things in the atmosphere like clouds, right? So clouds are going to reflect sunlight or solar radiation back to space. And also some of that gets down to the surface and bounces off things that are light at the surface, like ice. And so some portion, almost a third of the energy that comes in from the sun is reflected back to space right away. And we learned this term last time, albedo, which is like whiteness, right? And so if we look at the Earth from space, we can see where there's large albedo. So clouds are gonna be large in terms of their albedo, and the desert is gonna be large in terms of its albedo. It's light, and we have ice up here, so it's very light. So that's high albedo, high reflectivity, and it's by definition that these things are light, because if you're sitting out in space and you can see them, what you're seeing is sunlight reflected back to your eyes. And so it's just, your eyes are perfect detectors of sunlight and perfect detectors of albedo. So you will come across different terms for our different kinds of radiation. So the most common one, obviously what comes in from the sun, we just call light. But you'll also hear insolation sometimes. So that's not the pink stuff in your walls. It means incoming solar radiation. It's like a word that's jammed together of these three individual words. Incoming solar radiation. And then also shortwave radiation. And that's a nomenclature that I'll use a lot. Shortwave radiation is energy coming in from the sun. And so shortwave then is in contrast to what the Earth gives off. So you'll hear various terms for what the Earth gives off as well. You'll sometimes hear it called heat radiation or infrared radiation. And then here's the other end of the dichotomy here is long wave radiation. So comparing long wave radiation coming from the Earth to short wave radiation coming from the sun. So here's kind of a important physical question of why are these different? So the sun is just some thing in space, and the Earth is just something in space, and they're both apparently giving off radiation. And why is the sun giving off what we call shortwave radiation, and the Earth is giving off what we call long wave radiation? Or another way to say that is, why does the Earth give off longer wavelength radiation than the sun? So there's these two laws in physics that help explain this, and so these are laws that we'll come back to, but I'm just stating them here. So one is called Stefan Boltzmann's law, and one is called Wein's law. And what Stefan Boltzmann's law says is that warmer objects emit more radiation, which we can just think of as energy, than colder objects do. So if we think about the Earth and the sun is warmer, it's hotter than the Earth, and so it emits more radiation than the Earth does. And then Wein's law, so this is what is really important for the greenhouse effect, and I'll show you why. But Wein's law is that warm objects emit a higher proportion of their radiation at shorter wavelengths than cold objects. So if you think about the sun is the warm object and the Earth is the cold object, Wein's law is telling us that the sun is going to emit more radiation at short wavelengths, at shorter wavelengths than the Earth is. So this picture here actually kind of illustrates both of these laws. So what this picture is showing, and I'm not going to have you try to do this, but the kind of the discussion question you should be thinking about here is describe how turning on an electric stove demonstrates both of these laws, demonstrates both Stefan Boltzmann's law and Wein's law. And so I will just tell you here that what's going on is when the stove is off, the stove is emitting electromagnetic radiation because all objects emit electromagnetic radiation. But when the stove's off, it's emitting at a wavelength that your eyes can't see. But then when you turn the stove on, it starts emitting more radiation, which you could feel if you just like put your hand over it. And it's not just from conduction. It's not that it's heating up the air and then the air is touching your hand, because even if it was a vacuum, you'd be able to feel that radiation coming off of that stove. So that would be demonstrating Stefan Boltzmann's law. But then your eyes are now detecting that radiation, right? You're seeing red there when it's turned on. And what that's doing is it's telling you that it's getting warm enough such that some of that radiation has short enough wavelengths for your eyes to see. And so this is easier to think about when we go back to kind of our electromagnetic radiation spectrum type diagrams. So remember that light, which we have right here, so visible light is just a certain wavelength of electromagnetic radiation. And it's the same, electromagnetic radiation is, or we have different names for electromagnetic radiation depending on the wavelength, right? We can call it radio waves or microwaves or infrared waves or visible light or ultraviolet or X-rays or gamma rays. And the only difference between those is just the wavelength of radiation. So our eyes are tuned to see just this very specific wavelength of radiation, which we call light. And so what's happening with our stove is that when it's off, it's sitting over here in the infrared. So infra means like below, like infrastructure means like kind of sitting below the structure. It's like the fundamental thing, right? So infrared means it's below red. So we're at a wavelength that is, or we're at a frequency that's less than red. The wavelength is actually longer than red. And when we turn it on, the stove gets hot enough so that it's moving some of that radiation that's coming off of it is red, and our eyes are picking it up as red light that we can actually see. And so this whole digression is to bring it back to the Earth and the sun. And so if we put those things on here, the sun is emitting, it's very hot, it's emitting radiation, electromagnetic radiation right in this visible range. And it's of course not a coincidence that our eyes are tuned to see the radiation that happened to be the most prevalent on the Earth, right? So we see that radiation specifically because we evolved on the Earth. But so we can see that from the sun. And then the Earth is colder than that. It's not that it's not emitting radiation, it is, it's just that our eyes can't see it. And so that is the quick explanation for why the Earth gives off longer wavelength radiation than the sun. And that's this critical distinction for thinking about greenhouse gases. So the Earth is colder than the sun is kind of the quick explanation for why it gives off longer wave radiation. So the Earth is giving off this longer wavelength radiation, which I have drawn as red here. And the way that the diagram is drawn, it's unlike what's going on over here, where the light just passes through these molecules, right? Here, the radiation, the longer wavelength radiation, does not just pass through the molecules. The molecules, which are H2O, water vapor, CO2, carbon dioxide, and methane, CH4, they absorb this longer wavelength radiation. And we won't get into the actual physics at the molecular level of why that is, but just suffice it to say that the longer wavelength radiation interacts with these molecules in such a way that they actually absorb that energy. And then they re-emit it, but they re-emit it in all directions, including back down towards the surface of the Earth, as well as out to space. But it means that the Earth is going to be less efficient at radiating its energy to space if these molecules are in the way, absorbing it and interacting with this longer wavelength radiation. And something that really complicates things is that clouds are actually over here also. So clouds interact with this long wave radiation. They also, they have this albedo effect where they're reflecting solar radiation to space, but they are also interacting with long wave radiation from the Earth. So this is my first then discussion question. My definition here is just molecules that interact very little with shorter wavelength radiation coming from the sun, but absorb longer wavelength radiation coming from the Earth. So if a molecule absorbed long wave radiation coming from the Earth, but it also absorbed the short wave radiation coming from the sun, that would be a little bit more complicated because it wouldn't be clear that putting it in the atmosphere would cause a net warming effect. Okay, so if the Earth's energy budget, think of it like a financial budget, if the energy budget was balanced and thus temperature was not changing, how much energy would be coming from the long wave radiation at the top of the atmosphere? So what is this number here if it's balanced? So if it's balanced, that means the same amount that's coming in is leaving. And so the system is kind of naturally going to evolve to a state of equilibrium. And so it would be 342 minus 107, because that's what's actually coming in would be the 342, and you'd have to subtract off what's actually just reflected straight back to space. And so what's left over is 235 watts per meter squared. So that's an important concept in physical climate science, is the energy balance, the energy budget, that if you don't have any changes in the atmosphere, in the constituents of the atmosphere, in greenhouse gases or clouds or ice or all this other stuff, then you would have a situation where the system has basically evolved a long time ago to an equilibrium or to a balance, and so it's not going to be changing. Okay, so this whole class is about global warming. And so that means that we're talking about temperature, the Earth's average temperature in relation to this energy budget. And so what is temperature? Well, temperature is a measure of energy, and it's measured in terms of, the technical way to say it is the average kinetic energy of the molecules in a substance. And kinetic just means energy of motion. So really what this means is just how fast the molecules in something are moving. But the critical detail here is that temperature is a measure of energy. And so we've just defined here, all the energy coming in and all the energy leaving just in kind of three different components. And so this is this like really, really helpful kind of discovery in climate science that if you think about the temperature of the whole planet and thinking about kind of long periods of time, there's really only 3 ways that you can change the global average temperature. This hugely simplifies the problem of trying to attribute temperature change to various things, because you kind of come up with a bunch of proximate ways that temperature could change. But they're all going to come down to working through one of these 3 ways, which are just on this diagram. So you can change the amount of outgoing long wave radiation coming from the planet, or you can change the albedo, the reflected shortwave radiation, or you can change the amount of energy coming in from the sun. Those are the only 3 ways to change the Earth's average temperature over long periods of time. So all of the climate changes that have happened over long periods of time in the past have had to do with one of these components of the energy budget changing. This is my version of the most cohesive story to tell about contemporary global warming. And it starts 400 million years ago in a time period in geological history that we call the Devonian period. And at that time, much more carbon was in the atmosphere than is in the atmosphere today. So at that time, our concentration of CO2 in the atmosphere, instead of being like 410 parts per million, was about 5,000 parts per million. So way more CO2 in the atmosphere. And as we would expect from the physics we've talked about today, it was much warmer then. So it was about 10 degrees warmer at that time. And we'll talk more later about why that doesn't necessarily mean that it would be fine to warm the planet by a lot right now. It basically has to do with the rate of change versus the absolute temperature. But so there used to be a lot more greenhouse gases in the atmosphere, and it used to be a lot warmer. And so what happened? Well, basically, it's the story of plants. So plants were photosynthesizing. We talked a little bit about photosynthesis in the last lecture, and we'll talk more about it later. But so to put that equation up there again, you have CO2 from the atmosphere, and then plants use water and sunlight, and they create glucose, right? This sugar molecule. This is like the structure of the plants. And then they release oxygen to the atmosphere. But the point of bringing this up is to just trace this carbon molecule, right? So we have the CO2 in the atmosphere, and where does it end up? It ends up in the plant, in the structure of the plant. And so there's respiration going on too. The respiration is the reverse of photosynthesis. So usually the ecosystem on net is kind of putting as much carbon back into the atmosphere as it's taking out. But over long periods of time, some of that organic material gets buried. And so what's happening is that when those plants are buried, that carbon is being sequestered from the atmosphere, and it's going into the ground. It's going into the dirt. And so taken out of the atmosphere into the ground. And so thinking about it this way is easier than a lot of other ways. If you're just like realizing that carbon in this case is not being created or destroyed, it's just being moved around. So the plants are photosynthesizing, they're taking the carbon out of the atmosphere, they're putting it into their structures, and then things can happen where the plants don't fully decay when they die and they get buried. And so with them is the carbon. The carbon goes with the plants underground. And we call those hydrocarbons. So they lose their oxygen, but they still have their hydrogen. And so that's why they're called hydrocarbons. And these are our fossil fuels. Coal, oil, natural gas are just buried organic material, buried plants from hundreds of millions of years ago. And the carbon is then stored underground. And so then skip forward 400 million years to the 1800s. And at that time, we had 280 parts per million of CO2 in the atmosphere. And we discovered that there's all of these hydrocarbons underground that we can burn, we can light on fire. And it's essentially, you think about that photosynthesis equation, it's releasing energy that was like ancient sunlight. The energy came from the sun, and the plant used that energy and it stored it in the bonds of that glucose molecule. And so the energy is in the bonds of these molecules here that used to be sunlight. And we are discovering in the 1800s that we can take that and use it to power our society, to create electricity, and to use it in our cars, and we use it for industrial processes. And so we currently are putting about 9 gigatons of carbon that was sequestered underground into the atmosphere per year. And so last time we talked about, okay, where does that go? That some of it is taken up by the plants on the land surface. We call that the terrestrial biosphere. So some of this 9 goes into plants, and we can see plants actually getting greener because they are just taking up more of that carbon into their structures. And you can see that from space as plants essentially getting greener. And then some of that is going into the ocean, where it's causing ocean acidification. So about, so it's like half of what goes into the atmosphere stays in the atmosphere, half goes into the plants in the ocean, and of that half, about half is in the plants and half is in the ocean. So it's like 25, roughly 25, 50%. And so this portion is bad for what we were talking about today in terms of if we're worried about the Earth getting warmer, because what stays in the atmosphere is what is going to inhibit the Earth from radiating energy to space, right? So then this arrow here is getting smaller as we're putting more of this carbon that used to be in plant material underground into the atmosphere. And then this arrow is getting bigger. So we have more long wave radiation coming back down towards the surface and causing the surface to be warmer than it would be otherwise. So when we do this, when we put CO2 into the atmosphere, we cause a momentary imbalance here in our energy budget, right? Because we've reduced what's leaving. So we have the same amount coming in, but we have less going out. And so that's my third discussion question. When do you think temperature will stop warming after CO2 is increased? And if we were to, let's say, stop increasing CO2, so no longer burning fossil fuels, what would cause the Earth to stop warming? And the key is to think about the Stefan Boltzmann law that says that warmer objects emit more radiation than colder objects. So you have to think about that the Earth, you've created an energy imbalance where there's more energy coming in than leaving, and then that is going to warm up the Earth. And then eventually, as it's warming up more, it will be emitting more radiation. And so it can hypothetically then, turn off that imbalance. So as we're increasing greenhouse gases in the atmosphere, temperature is going up. But you have to think about, okay, what else is going to change once you start increasing temperature? So we have other things in the diagram that are also going to change. So the ice albedo feedback is an important feedback. So feedback here, again, we'll return to all these concepts in more detail later, but feedback means that you're increasing the temperature, you're doing something that's feeding back and increasing the temperature further. So ice albedo feedback would mean that you're increasing the temperature. Now you are decreasing your ice so that you have less albedo because you've decreased your ice. And so that's going to increase the temperature further. There's other important feedbacks. There's water vapor feedback. Water vapor, I already mentioned, was a greenhouse gas. It turns out that warmer air can hold more water vapor. So you get more evaporation when it's warmer. And so you release some of the water vapor from the ocean, it's into the atmosphere, then you have more greenhouse gases in the atmosphere because it's warmer, and then that can cause more evaporation. And so that's another one of these feedbacks that causes the Earth to get warmer than it would be otherwise if we didn't have these feedbacks. Cloud feedback. Cloud feedback is very important, but very complicated, and we don't actually even know the sign of the cloud feedback necessarily. And you can kind of get that sense from looking at this diagram that clouds have this cooling effect where they reflect radiation to space over here, but they also have this greenhouse effect where they absorb infrared radiation from the Earth. And so it would depend on exactly what type of clouds change in order to figure out if the cloud feedback is going to cause more warming than you would get otherwise or less warming. So cloud feedback is important, but we don't actually necessarily even know the direction that it causes, either enhanced warming or reduced warming. And then carbon feedbacks, again, talk more about, but it turns out that as it gets warmer, a lot of parts of the Earth's system end up releasing more greenhouse gases in the form of CO2 and methane into the atmosphere. So thawing permafrost is one of these things, that there's carbon stored in frozen ground in high latitudes and high altitudes. And as that melts, bacteria start eating the organic matter and releasing the carbon to the atmosphere. Also, as oceans get warmer, they start releasing carbon to the atmosphere. So all of these things are working to cause more warming than you would get otherwise. I'm going to skip over that video and just go to, these are kind of just the takeaways for today. So we talked about what a greenhouse gas is. So like the actual definition of a greenhouse gas in terms of our energy budget. And it has everything to do with shortwave and longwave electromagnetic radiation. And so greenhouse gases are gases. The definition of them is gases that do not interact or interact relatively little with the shortwave radiation coming from the sun, but they do interact a lot, or they absorb and re-emit longer wavelength electromagnetic radiation coming from the Earth. So selectively making it more difficult for the Earth to cool itself to space. And then looking at our energy budget diagram, there's only 3 ways to change the Earth's global average temperature by changing the Earth's energy budget. So we can, and again, I don't mean humans necessarily, but it could be that solar radiation changes. It could be that the amount of solar radiation reflected to space changes, or it could be that outgoing long-wave radiation via changes in the greenhouse effect changes. Those are the only 3 ways. So humans are enhancing the greenhouse effect by transferring carbon in the form of CO2 and methane was buried underground, transferring that into the atmosphere and enhancing the greenhouse effect. And then a lot of the warming that we're seeing contemporarily, global warming, is not actually caused directly by the increase in CO2 and methane. Most of it actually is caused by those feedbacks that I just kind of flipped through quickly at the end there. So water vapor feedback in particular, but also the ice albedo feedback and these other feedbacks actually are responsible for most of the warming that we're seeing today. So that is my section today.